This poster serves as an introduction to a homebrew video game console made from scratch, using a lot of inspiration from retro consoles and modern projects, but with a unique architecture. Some friends of mine have told me again and again not to keep this project to myself and to put this information online. So here it goes. My name is Sérgio Vieira, and I am a Portuguese guy who grew up in the 80s and 90s. I have always been nostalgic towards retro gaming, specifically the third and fourth generation consoles. A few years ago, I have decided to learn more about electronics and try to build my own video game console. Professionally, I work as a software engineer and had no experience with electronics other than occasionally building and upgrading my desktop computer, which does not really count. Even though I had no experience, I said to myself, why not? Bought a few books, a few electronics kits, and started to learn what I felt I needed to learn. I wanted to build a console that would be similar to those which are nostalgic to me. I wanted something between an NES and a Super Nintendo, between a Sega Master System and a Mega Drive. These video game consoles had a CPU, a custom video chip. In those days it was not called a PPU, and an audio chip, either integrated or separate. Games were distributed in cartridges, which were basically hardware extensions with a ROM chip and sometimes other components as well. The initial plan was to build a console with the following characteristics. The reason I wanted SD card support instead of cartridge support is mainly because it's a lot more practical to have programs available in an SD card, as it makes it a lot easier to copy files from a PC to it. Having cartridges would mean to make it more hardware and to have a no hardware for each program. The first thing I worked on was the video signal generation. Each video game console of the era I was aiming for had different proprietary graphics chips, which made them all have different characteristics. For this reason, I did not want to use any pre-made graphics chip. I wanted my console to have unique graphical capabilities, and because it was impossible for me to make my own chip, and I did not know how to use an FPGA, I opted for a software-based graphics chip, using a 20MHz 8-bit microcontroller. It's not overkill and has just enough performance to generate the kind of graphics I want. So, I started by using an Amiga 644 microcontroller running at 20MHz to send up a video signal to a TV. Because the microcontroller does not support this protocol natively, I had to bit-bang the PPU video signal protocol. The microcontroller produces 8-bit color, RGB 332, 3 bits for red, 3 bits for green and 2 bits for blue. And a passive deck is used to convert this to analog RGB. Luckily in Portugal, one common way to connect an external device to a TV is through a SCART connector, and most TVs accept RGB input through SCART. Because I wanted to have a microcontroller only drive the TV signal, I call it the PPU Video Processing Unit. I decided to use a double buffer technique. I had the second microcontroller, PPU Picture Processing Unit, which is an Amiga 1284, also at 20MHz, generate an image to a RAM chip VRAM, while the first one would dump the contents of another RAM chip VRAM to the TV. After 1 frame, 2 frames, in PPU, a 1/25th of a second, the PPU switches the RAMs and dumps the image generated into RAM 1. While the PPU generates an image to RAM 2, the video board turned out quite complex, as I had to use some external hardware to allow for the two microcontrollers to access the same RAM chips, and also to speed up the access to RAM that also had to be data-banked. So I added some 75 series chips such as counters, line selectors, transceivers, etc. The firmware for PPU, and especially the PPU, also became quite complex, as I had to do extremely performant code to be able to have all the graphical capabilities I wanted. Originally it was all done in assembly. Later I coded some of it in C. I ended up having the PPU generated to 25x192 pixel image that is then sent to the TV by the PPU. This resolution might seem low, but it is in fact only a bit lower than the consoles mentioned above, that usually had resolutions of 256x to 25 pixels. The lower resolution allowed me to cram more graphical features into the time I had to draw each frame. Just like in the old days, the PPU has fixed capabilities that can be configured. The background that can be rendered is composed of 8x8 pixel characters, sometimes called tiles. This means the screen background has the size of 2 8x25 tiles. In order to have per pixel scrolling and the ability to update the background seamlessly, I made it so there are 4 virtual screens, each one having 2 8x25 tiles that are contiguous and wrap around one another. Above the background, the PPU can render 64 sprites that can have a width and height of either 8 or 16 pixels, 1, 2 or 4 characters, and can be flipped horizontally or vertically, or in both axes. Also above the background, an overlay can be rendered, which is a patch composed of 2 8x6 tiles. This is useful for games that need a HUD and in which the background is scrolling and the sprites are being used for other purposes than to show information. Other advanced feature is the ability to scroll the background in different directions in separate lines. This enables games to have effects such as a limited parallax scrolling or split screen. And there's also the attribute table, which is the possibility of giving each tile a value from 0 to 3, and then it's possible to set all the tiles of a given attribute to a certain tile page, or increment their character number. This is useful when there are certain parts of the background that change constantly. The CPU does not need to update each one of the tiles. It only needs to say something like, all tiles with that attribute 1 will increment their character number by 2, using different techniques. This effect can be seen, for example, in block tiles with a moving question mark in Mario games, or in waterfall tiles that seem to be changing constantly seen in other games. After having a functional video board, I started working with the CPU I chose for the console, Zilog Z80. One of the reasons I chose the Z80, other than it just being a cool, retro CPU, was because the Z80 has access to a 16-bit memory space, and a 16-bit I/O space, something that other similar 8-bit CPUs do not have, such as the famous 650 the 6502, for example, only has a 16-bit memory space, which means that the whole 16 bits were not reserved just for memory, but had to be shared between memory access and external device access, such as video, audio, inputs, etc. By having an I/O space together with a memory space, I could have the whole of the 16-bit memory space reserved for memory, 64 KB of code and data, and have the I/O space for communication with external devices. I started by connecting the CPU to an EEPROM with some test code, and also connecting each wire the I/O space to a microcontroller I had set up to communicate with the PC wires to in order to track if the CPU was functioning well as all the connections I was making. This microcontroller, an Atmec 324 operating at 10 MHz, was to become the IOMGU, or input-output microcontroller unit, responsible for managing access to the game controllers, SD card, pins to keyboard, and the RS to through communication. The CPU was then connected to a 128 KB RAM chip, from which 56 KB was accessible. This seems like waste, but I could only get either 128 KB or 32 KB RAM chips. This way the CPU's memory space is composed of 8 KB of RAM and 56 KB of RAM. After this I updated the IOMECA's firmware with the help of this library and added SD card support.